What is up, everyone? In this video, we're going to talk about the emission spectra of atoms and also the Bohr model of the atom. The Bohr model was the first of its kind because it was the first model to suggest that the energy of electrons is quantized, meaning that the energy of an electron in an atom is limited to certain discrete values. And it's the emission spectra of atoms that led to this model. So what exactly is an emission spectrum? Well, it all originates from how atoms behave when they absorb energy. When atoms absorb energy in the form of heat, light, or electricity, oftentimes they're going to re-emit that energy in the form of light. These images show light emitted by nitrogen, neon, and krypton atoms. Notice that each element gives off its own characteristic color of light. But why? Well, if we inspect this light more closely, we'll discover a very revealing clue that shows how electrons exist within atoms. By now you probably know that passing light through a prism will separate the light into its constituent wavelengths, but unlike the continuous white light spectrum that is observed from the sun or a light bulb, the spectrum of light given off by atoms, the so-called emission spectrum, is composed of specific bright lines with dark spots in between. This type of spectrum is called a line spectrum. Each element has its own unique emission spectrum. Think of it like a fingerprint. In the same way that a fingerprint can be used to identify a person, an emission spectrum can be used to identify an element. In fact, astrophysicists can identify the elements that make up a star by obtaining the emission spectra from the light given off by these stars. But how exactly did emission spectra change the way that we think about atomic structure? Well, according to classical physics, which treats electrons solely as particles and light solely as waves, an atom made up of an electron orbiting a nucleus should emit a continuous white light spectrum, not the line spectrum that it actually emits. In 1888, Johann Rydberg, a Swedish mathematician, came up with an equation that accurately predicted the wavelengths of light emitted by a hydrogen atom. In his equation, 1 over the wavelength is equal to r, which is the Rydberg constant, 1.097 times 10 to the 7th inverse meters, times the quantity of 1 over m squared minus 1 over n squared, where m and n are integers. If you'd like to see this equation in action, please let me know. But this equation alone couldn't explain the discrepancy between the predictions of classical physics and the observed reality. That's where Niels Bohr comes in. Bohr proposed a model in which electrons could only exist in certain orbits at certain fixed distances from the nucleus. He also argued that the energy of an electron was also limited to certain discrete values. In other words, the location and energy of electrons is quantized. It's sort of like a ladder. Just as your feet can only stand on the rungs of a ladder, but not in between, electrons can exist only in these orbits, but not in between them. Furthermore, his model suggested that an electron orbiting a nucleus does not absorb or emit energy. It's only when an electron makes a transition or a jump between orbits that an electron absorbs or emits energy. Electrons absorb energy by jumping from an orbit of lower energy to an orbit of higher energy, while electrons emit energy by jumping from an orbit of higher energy to an orbit of lower energy. The amount of energy absorbed or emitted is simply the difference in energy between the two orbits. Since the electrons are never observed between orbits, the jump from one orbit to another orbit is instantaneous. The electrons literally teleport between orbits. Let's examine the emission lines of the hydrogen spectrum. A transition from the third orbit to the second orbit emits red light at a wavelength of 656 nanometers. A transition from the fourth orbit to the second orbit emits blue-green light at a wavelength of 486 nanometers. Jumping from the fifth orbit to the second orbit emits blue-violet light at a wavelength of 434 nanometers. And finally, a jump from the sixth orbit to the second orbit emits violet light at a wavelength of 410 nanometers. Notice that as the energy of the transition increases, the wavelength of the emitted light decreases. There are several more transitions that occur within the atom, but only the ones that we just discussed emit wavelengths of visible light. All other transitions emit light with wavelengths that lie outside of the 400 to 700 nanometer range of the visible spectrum. Nevertheless, only certain specific amounts of energy are emitted as an electron relaxes to a lower energy orbit. These packets of energy, also called quanta of energy are emitted in the form of photons, or light particles. The energy of each photon is related to the wavelength of the light according to the equation E equals hc over lambda. Since the atom emits only a series of photons with specific energies, there are only going to be specific wavelengths of light that show up in an atom's emission spectrum. And that's why we get a series of bright lines instead of a continuous white light spectrum. So the Bohr model had a lot of explanatory power, but a lot of questions were still unanswered, like why electrons could only exist in certain fixed orbits. Well, it turns out that these orbits are actually the result of electrons behaving as waves, and we're going to expand upon that in another video. The Bohr model is not the model that we currently accept today, but it's still really important because it served as an intermediate model between the classical understanding of the electron and the fully quantum mechanical interpretation. The Bohr